Hello, hello, hello. This is Trent video number 1, dedicated to a specific viewer out there, Trent Graham Warnock. And Trent has said, well, I want to learn calculus from the ground up. Can you teach me? I guess that's a little bit of a tall order, but I mean, I would enjoy it. So I think if he or somebody else wants me to go through calculus, then I'll go through calculus. Where do I start? Well, I start with limits. You just can't go anywhere in calculus without limits. Everything is defined through a limit in calculus, including derivatives and integrals. So, this is different the way I go about them, but I really do start with the formal definition first. And the formal definition is if we have a function f of x and it's continuous, maybe I should say what I mean by continuous first so there is no ambiguity. Well, what I mean by, for now we can think of continuity, and this is a pretty big idea in Calc. Continuity, and usually we're considering some interval. So let's say the interval from x equals a, I still had my thing on, from x equals a to x equals b. This is the interval we're talking about, and we're wanting to see if it's continuous. The loose definition I'm going to give for now, since I haven't actually defined a limit yet, is a function f of x is continuous on a to b if you can hold your pencil starting on a and draw the function without having to lift up your pencil at all to b. Without, you don't have to lift your pencil from the paper, and there's no, sharp turns or anything like this. So this is, for now, what I'm going to define as continuity. So now, the limit, we're concerned about, we write it as the limit as x approaches a, some value, some constant a, of f of x, and we're going to say it's equal to some number L. So if f is continuous, the function f is continuous on x being some element, that's what this symbol means right here, is an element of, for x being an element of the open interval from a to b. So these parentheses here are open intervals, meaning it's from the interval from a to b, but it's not including the points at a and at b. So if f of x is continuous on a to b, but maybe it's not continuous right at a. So if for all, that's what this upside down a means, for all. It's set theory notation for all. If for all epsilon greater than 0, there exists, that's what this reflected e means, there exists some delta such that the absolute value of f of x minus L, so where L is the answer to our limit, is less than delta for all 0 being between the absolute value of x minus a being between epsilon. So you're probably like clear as mud, right? So what this is actually saying now, let me draw a graph here. And we're going to assume that the function is continuous on the entire interval from a to b, so including a and including b, although we don't need to make that assumption. I'm just doing it here because I want to, I guess. Let's say we have this curve right here, and it's an exponential curve, it looks like. Let's call this function f of x, I guess it's a function of x. And so let's say we are approaching this point here, x, on this curve. So then the y value then is f of x, Okay, so now what we are talking about with this epsilon and delta business is, so 0 is less than, the absolute value of x minus a is less than epsilon. So what this means is that we can go, we can go a little distance over, and I'll call it epsilon. We can go a little distance over x, or we can go a little this should be a minus, a little distance under x. So we have x minus epsilon and x plus epsilon. And now, obviously, these points here would be f of x minus epsilon. And this point here would be the y-coordinate f of x plus epsilon. In other words, we would say, since I introduced this delta, we would say that f of x plus epsilon is just going to be f of x plus a little distance delta. And f of x minus epsilon is going to be f of x minus that same little distance delta. Now, it's not entirely rigorous what I mean by a little distance, but the point is that it can be as small of a distance as I want. See, we're letting epsilon go to 0. In other words, we want to, if our whole limit answer is going to be f of x, from an intuitive standpoint, we know that the limit as, well, I'm going to be saying as x approaches x. Hopefully, what I mean, this is not standard notation, but what I mean is that as we get to this point here, this x value here, maybe I will call it c. Let's call this c. So then this would be c minus epsilon, c plus epsilon, f of c plus epsilon, f of c, and f of c minus epsilon. So we could say that the limit as x approaches c of f of x is just f of c. Now, this is true just from intuitive standpoint. I mean, just looking at it, right? The function is continuous. So if we want to find what functional value do we approach as x approaches this constant c, well, just plug in c into the graph since the function is continuous. And it should make sense that, let me clean up this a little bit so I can have some room to work with. Oh, oop. I didn't want to erase that dot, but whatever. So as our x values, this is c right here. As our x values squeeze in and they get closer and closer to c, then what happens is our y values, our f values, our functional values, whatever you want to call them, they would approach, since the function is continuous, they would approach f of c. And so this is what we were talking about with limits. It's all about what the function approaches, not what the functional value actually is. What I mean by this is, so I picked the simplest of examples where the function is continuous. If we're taking the limit of any continuous curve, and, I mean, for example, if we want the limit as x approaches 1 of f of x, and let's say f of x in this example, just for this specific one here, is a parabola, x squared. Okay, we graph x squared, and it goes like that, more or less. That's kind of a really bad parabola, actually. And so we look at this curve, and let's say this is 1, and we look at, well, what's f of 1? Because we can just plug that in since the function's continuous. We don't have to mess with it any because the limit is existent. It's a nice curve. We would just say that this is just f of 1, which is 1 squared or just 1. And so the limit as x approaches 1 of x squared would be 1 in this case. Now, the interesting thing to note that I kind of alluded to before, I guess, is let's say we had this. So we had a piecewise function, f of x, being equal to two different things here. So it's equal to x squared for x not equal to 1. So it's x squared. It's a parabola basically for every x value except for 1. But at 1, it's undefined. There's no value that you can plug in at x equals 1. But everywhere else, it's a parabola, the parabola x squared. What we would obviously be asking, since math people like to make things more complicated, right, is we have this function here that we're considering now. And since the only place that it's wacky at is at x equals 1, let's find out what the limit is at x equals 1 of this function f of x, this piecewise defined function. And why are they called piecewise defined functions? Well, because they're made up of two or more pieces. You've got this piece and you've got this piece. And they both tell you information about the function. So what is this limit? Well, it is still going to be equal to 1. Why? Because with limits, it does not matter what the actual functional value is, only what the functional value approaches. And I hope you could kind of see that from this definition here. See, we can let epsilon get as small as we want, with the condition that it's greater than 0. And we therefore would have delta be getting as small as it can be with the condition that delta is greater than 0. So in other words, delta can't be equal to 0 though. So we're never actually looking at the functional value f of c itself. We're looking at what happens to f of x as x approaches c. So the limit, if we're taking the limit at some value where the function isn't defined, that's okay. The limit can still exist. The function need not be defined at the value you're taking the limit at. As another example, if I have this exponential curve, now if I erase it, it's going to erase the whole thing. Let me go like this, and let's say this is c, and this is the curve f of x. Then we would say in general that the limit as x approaches c of this curve f of x, it is still just f of c. Because now I know it's not defined at f of c, but as you approach c, the function approaches f of c. And this is all the limit is concerned about, is what does my function approach, not what it actually is at that value. What does it approach? Now there's a couple other things in limits I want to mention. They are called, up to this point, I've been talking about only two-sided limits. Why are they called two-sided limits? Because I have considered approaching from both sides, from the left of c and from the right of c. And whichever way I approach from c, I still get the same answer, which in the case of this function was f of c. And that was my answer. Now, this is not always the case. This is why we have a thing called one-sided limits. And you could probably guess that we're just considering limits from only one side of c, from the left or either from the right. So let me do an example. Let's draw this. And they tend to give you piecewise functions. That's why I'm kind of doing piecewise functions. Let's say we have, this is x equals 1, and let's say we have this exponential looking function, and it's an open circle at x equals 1, so it's not defined at that particular point. But then say it's a closed circle here, and it just goes like that. So it's like this exponential logarithmic piecewise function. And here it asymptotes at 0 or something like this. So we would be probably interested. Now, anywhere else along this curve except at x equals 1, the limit is obvious. Just plug in that functional value. For example, if this is the point x equals 2, and this is the curve f of x, which is also part of this curve because it's a piecewise function, it's just a different piece of the part. If we were concerned about the limit as x approaches 2 of f of x, well, that would just be f of 2, since the function is continuous at x equals 2, and anywhere in some interval containing 2 that is greater than this 1 right here. Now, what we would be interested, though, is probably the limit as x approaches 1 of f of x. And as I've written this limit now, this limit actually does not exist, and we write that as dne, usually does not exist. Why does it not exist? Because you get two different values when you approach from two different directions. If I approach x equals 1 from the left, over here, then, let's call this value 1, and let's call this value 3 on the y-axis. As I approach 1 from the left, x equals 1 from the left, then what I'm approaching here is this y equals 1. But if I approach x equals 1 from the right, then what I'm approaching here is this y equals 3. I'm getting nowhere closer to this x equals 1 if I approach from the right of x equals 1. And likewise, I'm getting no closer to this to this y equals 3 right here if I approach from the left of x equals 1. So since what we call the one-sided limits, right, approaching from the left and from the right-hand side of x equals 1, since those aren't the same value, the two-sided limit, this limit here, cannot exist, because in order for it to exist, the one-sided limits would have to be equal. Now, we could consider the limit as x approaches 1, and we write it like this with a little minus exponent on top of the 1. And this is read as the limit as x approaches 1 from the left. And so what this means is we're only considering the limit of f of x. We have to actually define the function we're taking the limit of. This is only asking about what's the value that we get closer and closer to on f of x as we approach 1, only from the left of 1. So that, in other words, is talking about just as I approach from this direction here. And it should be obvious that as I approach that direction, my x value is just 1. So that limit there is 1. Now the limit as x approaches 1, and we write it with a plus sign here, as an exponent of f of x, this is read the limit as x approaches 1 from the right. So that would be going in this direction. And it should be obvious that the value that we approach is this this 3 right here. So this whole limit is equal to 3. Now, a thing I want to point out is that it did not matter whether this was an open circle or a closed circle. For example, I could make this a closed circle. The limit would still be 3. This limit right here would still be 3 because, again, the function doesn't need to be defined at the point you're taking the limit at, because the limit is only concerned with what the function approaches. That's the key idea of limits. It's all about what the function approaches, if you haven't picked up on how many times I've said approaches already. Anyways, so those are one-sided limits, and now maybe the more rigorous definition of continuity, I said at the beginning of the video, you could just, trace your pencil without having to lift your pencil up from A to B, and that is what I would define as continuous. What I will now define as continuous, since I have a rigorous definition of the limit, and since now we have limits as a part of our toolbox, we say that, and this is for continuity at a point. So we want to check if a function is continuous at a point. We say, let's say continuity at the point at x equals a. So we define a function to be continuous at the value x equals a if the limit as x approaches a of f of x is equal to f of a. So this makes actually 3 assumptions. It first of all makes that f of a is defined, right? Because it needs to be equal to this, which also needs to be defined. It makes another assumption that the limit exists, right? The limit has to be existent. And it also makes the assumption, since this is not a one-sided limit, this is a two-sided limit, since we don't have that little minus or the little plus, it also makes the assumption that the one-sided limits are equal to each other. And you can hopefully see how this is consistent with my kind of lax definition, I guess, of continuity I gave at the beginning. Because again, if I have this curve here, okay, and this is A, well, this value right here is f of A, and f of A is also the limit as x approaches A of f of x, since the, well, I don't want to say since the curve is continuous, because that would be kind of circular reasoning, but as x approaches A, either from the left or from the right, it should be pretty intuitive that you approach f of A on the graph. And so this is the rigorous definition of continuity at a point. Just one more type I would want to give. One more type I want to give is, let's consider this weird trig graph. Let's say it goes something like this, but then you get inside, and it oscillates more and more and more. And it's oscillating, and then as the farther you go out, it just tends to spread out more. Now, there is a function that would actually model this trig graph. For example, it could be a cosine of 1 over x. Cosine of 1 over x. Because as x gets closer to 0, the cosine will repeat in periods quicker, since you'd be approaching 1 over 0, which is undefined. So let's consider the limit as x approaches 0 of this function that I've written here, f of x, this cosine of 1 over x. And I could just write it as, since I guess should get used with new notation, cosine of 1 over x. The limit as x approaches 0 of cosine of 1 over x. Well, look at the graph with me. This function is continuous for all values x except at 0, because we would then have cosine of 1 over 0, and 1 over 0 is undefined. So it would not be defined at 0, but it would be defined at every other x value except for 0. And of course, as mathematicians, we want to find the limit at the one value it's not defined at. So at x equals 0, or as x approaches 0, the cosine of 1 over x, that limit. Well, this is a pretty poorly drawn graph, but the idea is that this function, it doesn't approach any value at x equals 0, right? Because it just gets infinitely more oscillating. It just goes back and forth like this. It doesn't approach any specific value. And they'll usually give this type of graph in any standard calc text. And so if you see this type of function at that weird point, this limit does not exist. Now, I did mention that 1 over 0, that 1 over 0 is undefined. Now, let's take a look at why that is, because a lot of times people don't know why that is. If we consider the graph of 1 over x, this is a hyperbola actually, and so it looks something like this, roughly. And so it's a hyperbola, y equals 1 over x, or xy equals 1. And so if we look, this asymptote here is at 0, obviously. And so we want to find or see if there is a limit as x approaches 0 of 1 over x. Well, no, right? Because as there is no, this limit does not exist, because as this is the point 0 right here, as I approach from the left of 0, I go down and down to negative infinity, and as I approach from the right of 0, I go up and up to positive infinity. So this limit does not exist, which, by the way, is why 1 over 0 is undefined, for the same, because 1 over x, as x goes to 0, well, that becomes 1 over 0. But if I were to take the limit as x approaches 0 plus of 1 over x, that would be equal to infinity. Sometimes, and I don't like this notation, sometimes calc texts will write, they'll interchange infinity and do not exist, because technically, infinity is not a constant. So they'll write does not exist because it just goes up and up and up. But you really should write infinity. It tells you more information. Here in this first case, the limit really does not exist. It doesn't approach anything. It goes up to positive infinity or down to negative infinity, depending upon which side of 0 you approach. But if you are given that you approach from the right, from this positive direction, I shouldn't say from the positive direction, because, for example, I noticed this in my class. If I had -1, sometimes people will say, well, if I approach -1, all the plus sign means as an exponent is either from the right or from the left. So although -1 is a negative number, if we approach it from the right, we're still approaching technically in the negative x-axis, because we're coming from here, which is still negative. But if it's a negative number there, all that exponent is read as from the left or from the right. Now, if we were to take the limit as x approaches 0 from the left of 1 over x, we get negative infinity. And so this is why 1 over 0, from a calculus standpoint, is not defined, because its limits are not defined and it's not continuous. The function 1 over x, that would model 1 over 0 as x approaches 0. Okay, now sometimes you can